All right, this is section 9.2, periodic trends in atomic size. So we're going to talk about how the elements change in size. First of all, here's our objectives, just kind of quickly looking at all these. Be able to define atomic radius, the shielding effect, describe factors that determine the trend in atomic size, and general trends for both groups and periods, and then use those to predict relative sizes of atoms and describe the variations that occur in these trends of atomic size in the transition metals. When we're talking about the elements, there's a lot of physical properties that are trend-like, that they tend to follow some kind of pattern as you move across the periodic table or down the periodic table. So as you move down or across, you have some trends that take place. There are three factors that usually affect this, and the first is how many protons you have. So the number of protons, known as the nuclear charge, is the first factor that affects that. The second one is the number of energy levels holding electrons, and the number of electrons in the outer energy levels. So how many levels are there altogether, and how many are in that outer level? That outer level is really kind of the really big important factor of all those things. So the number of electrons held between the nucleus and the valence electrons is a third factor. This is known as the shielding effect. So if we talk about our valence electrons, so we're talking about, let's say we got sodium, and it's got 2 electrons that go in the first level. It's got 8 that go in the second level. And then it's got 1 more in that third level. And so they're talking about, this is the valence electron, this one right here. All of these other ones tend to shield it. So, if we're talking about size, atomic size, the distance from the nucleus to the valence shell. Now think about that, to the valence shell. Well, how do we know where those electrons are going to be? When we talked about, we don't even really know what it is exactly at any time. So how do we figure that out? It's pretty hard to determine that when you're talking about a probability distribution and not like where an electron is exactly. So because there's no well-defined outer edge of the electron cloud, we have to do things in a little bit different manner when we're trying to figure this out. You're not just going to take a ruler to it and measure it. So one of the ways, and probably the only way we'll really get into, is that they talk about atomic radius when we have 2 what they call homonuclear diatomic, a homonuclear diatomic molecule. Basically what we're saying is we've got 2 of the same thing bonded together, and then what we're going to do is we're going to measure. We can tell where the nucleus is. That's one thing we can tell. So we're going to measure how far it is between those 2 nuclei. And we're going to assume that halfway in between, that's our radius. Okay, so made up of exactly 2 atoms. That's what a diatomic molecule is. This term, very important that you understand diatomic. We're going to talk about that a lot here coming up in the next chapters. Okay, so make sure that you're familiar with that term. Homonuclear means that they're both the same thing. So it's both Fs, both fluorines, not like 1 hydrogen, 1 fluorine. All right, I want you to stop the video and I want you to take a look at the atomic radii as you go down. Group trends is what we're talking about here. So group trends mean as we go down. So I want you to look. So let's say you pick this one right here and look what happens to the size. Now if you cannot read this on this screen, then go to ptable.com and you want to use the calculated radius. That's what I'm doing. It may not say calculated depending on which of these other buttons over here has been pushed, but it's going to be that top one on that second column. Click on that, click on calculated, and then just take a look. And I want you on your outline, on your slides, I want you to write a rule that you see that happens as you go down the chart in general. So write a rule. All right, so each period in the periodic table means we're adding an energy level. So if we're talking about elements as we go down, let's say we're looking at lithium, we've got our nucleus. It's got 1, 2, and then 1 in the next. Well, we already did sodium. Sodium's the next one. So it's got 2 in the first. It's got 8 now in the second. And it now has a third. So you'll notice that each time we're going down, we are adding a level. Okay, that's important because think about it. If you're adding levels, what's happening to my size? It's moving out, right? It's getting bigger. Second factor is what's known as shielding. Shielding is when those electrons that are in between, the core electrons, anything that's not a valence electron tends to shield those outer electrons. So, we've got our sodium, and that first level, hey, it's providing some shielding. That second level is providing some shielding. And so this third level, these guys can get away a little bit farther because there's some shielding, between the positive nucleus here and this negative electron. And the more levels you have, the more electrons you have in there, the more shielding you have. The more shielding, the farther this one can sneak away. It's just these guys, these protons just can't pull it in quite as much. So shielding depends mostly on the number of electrons that you have between the nucleus and the valence electron. So as you add more and more levels, you get more and more shielding. More shielding, the farther the electron can spread out. Therefore, that's a direct trend. The more levels you add, the bigger the atom gets. So as you go down a group, and you'll see that we've got our chart here, as you go down, that would increase in size. Now here's what I suggest that you do. On your own periodic table, get your blue periodic table and write these trends down on that table. And the way that I do it is just kind of what they did there. I would write an arrow pointing down, and we're talking about atomic size. And I would always write my arrow so that it gets bigger based on, where the arrow is pointing. So the biggest one would be at the bottom here. So as you go down from helium, neon, argon, all those guys get bigger as you go down. So the increase in the number of energy levels means that these electron clouds take up more space, they get bigger. Okay, once again, take a look now, and let's take a look at periodic trends. Whenever they talk about periodic trends, they're talking about as you go across the chart. So I want you to look at those numbers again and see what's happening in general. Now this is a little bit harder. In fact, actually the ones that I picked there are not very good. You're better off coming up to the ones before the transition metals, because the transition metals kind of mess things up a little bit. So look what happens here as you're going across, and notice what's happening to your size. Once again, if you can't read it, go to ptable.com, but I want you to write what you think the trend is in your notes next to the slide. So did you notice that it actually went down as you went across? So look at this. As we're adding protons, notice that the size was going down. Now, most people think, hey, if I'm going to add more electrons, more protons, it's going to spread out. It's got more, okay? But we're not adding levels. That's the key, not a new level. And so what happens is, what I've got now, if I go to this one at 10, neon, versus, let's say, number 3, lithium, I have 10 protons, 10 electrons. These protons, they can pull that in quite a bit. I'm not adding more levels, so therefore there's no more shielding, so they can pull it down quite a bit. So the number of energy levels is the same, but the electrons increases. And since you've got more protons now, they're pulling harder, making the atoms smaller. So it's a little bit non-intuitive sometimes on this one, but as you go across the periodic table, as you go from left to right, they get smaller. So atomic size decreases going across. Now, in my periodic table, you know, we had our one, and I always said, hey, we draw it so that it points to the biggest one. So I would draw across the top another arrow, because as you go from right to left, you get bigger. So this one's small. So in the top right corner, helium, that's the smallest one. Down here in the bottom left-hand corner, francium, that's the biggest one. Okay? So here we go. Okay, you can see this, and I usually draw the arrow across the top, but you can draw it across the bottom if you want to, and you can see how it gets bigger as you go to the left and bigger as you go to the bottom. And I would draw these in. I put them on your periodic table so you know these trends. We're going to have several different trends when we're all done, and it's important that you know these. And you know, obviously, you're not going to get to use your periodic table, but it's a good way to study. The transition elements, they're a little trickier. Notice the trend here. Okay. And in general, it's down, but you know, it goes up here. It goes up a little bit here and here. So it's not quite as perfect. So, you know, you've got more protons, therefore the charge is increasing. So it's roughly the same way, but it's not as close. You know, it doesn't follow it as closely because, you know, you're adding things to the D level, which is actually inside, so it actually can provide some shielding and stuff. So it's not a perfect thing. It's just a general. So while you're increasing the nuclear charge, you're also increasing the shielding. Okay, so this would be a good point to know. This might be a great test question. I would say, why doesn't the transition, why don't they follow this trend as well? You would say, well, they would add nuclear charge, but they also increase shielding. So those two things kind of counteract each other. And there you have the end of section 9.2.